Today in the workshop, we're working with 4-pin computer fans. You'll see how these PWM controlled fans work and how we can control their speed and read their internal tachometer using an ESP32. We'll also build a temperature controlled fan driver with an OLED display and stall protection. We've got a nice breeze in here today, so welcome to the workshop. Well, hello and welcome to the workshop, and today we are going to be working with the little cooling fans that you use in computer power supplies and on heat sinks in computers. I'm just going to call it a computer fan. Now, when you first think about it, the fan doesn't seem like much. It's just a motor that turns a blade, but computer fans are actually pretty complicated devices. These are brushless DC motors, and they have an integrated electronic speed control. And on some of these fans, you can get back a reading for the tachometer to see how fast the fan is turning, and you can also control their speed using pulse width modulation, and that's exactly what we're going to be doing today. We're going to see how these fans work, and we're going to see how we can use an ESP32 to both control the speed and monitor the speed of the fan. Then we're going to wrap everything up by building a project, which is a fan controller that includes a temperature sensor that can turn the fan on at a specific speed at the specific temperature, and even monitor the fan to make sure it's okay, and give you an alert if something happens to the fan and cut the power off the fan as well. So it's a handy device we're going to create at the end of the video. But we're going to start off right now by learning everything we can about computer fans. DC computer fans are driven by brushless DC motors, and they have integrated electronic speed controls. 5 and 12 volt DC fans are the most common, but you can also get 24 and 48 volt fans as well. There are a few key parameters to check for when looking for a DC computer fan. The first one is the fan's speed, and they're available with maximum speeds of 1,000 to over 5,000 RPM. The airflow is another important specification, and depending upon the fan's size, they can be as little as 30 to as much as 150 cubic feet per minute of airflow. These fans also come in standard sizes ranging from 25 by 25 millimeters to 200 by 200. DC computer fans are available with 3 different types of connections: a 2-wire, 3-wire, and 4-wire connection. The 2-wire connection has power and ground only. The fan is driven at a fixed speed, and it does not support external PWM control. The 3-wire devices adds a lead for the tachometer. This tachometer provides 2 pulses per rotation of the fan. This is used not only to measure the fan's speed, but also to detect a stalled fan. With the 4-wire fan, an additional connection has been made for a PWM input. You can use this input to vary the speed of the fan, and this is the type of fan that we're going to be working with today. DC computer fan speeds are controlled with pulse width modulation. Most of these fans use a 25 kHz pulse signal. The width of the pulse controls the speed of the fan. A wider pulse will spin the fan faster. A 0 or grounded pulse will stop the fan. Today we're going to do some experiments using an ESP32 and a 4-pin DC fan. So let's go take a look at a few fans now. And we'll just take a quick look at a few computer fans over here. Now, this is a pretty standard one. This is the 120 millimeter size, which is probably the most common, and it's a 12 volt PWM fan. And I've got 2 smaller fans at the front over here. They're very nice ones, but they're not identical, even though they might look identical. They are both 5 volt fans, and they both consume the same amount of current, and they produce the same amount of airflow. But this fan here has only got a 3-pin connector on it, so it only has a tachometer connection, but it does not have the connection for the PWM signal. So this is not the type of fan we'll be using today. We'll be using this type, or this type over here, which has the 4-pin connector, which includes the PWM connection. Now, one thing you should note is there's no standard for the color codes on the wire. For example, on this one here, the positive voltage is yellow. On this one here, it's red. On this one, all 4 wires are black, so you need to go by the connector, and the connectors are all keyed, and they've got pin 1 marked off. So just go by the connector and not the color code wires when you're wiring up your fans. Okay, I've got a demonstration hooked up for you with a small PWM computer fan, which you can see hanging in midair over here. And I'm not sure if you can tell, but it actually is on right now. If you look through the sides, perhaps you can see the blade spinning. Now at the back, you can see we have an oscilloscope over here, and this is illustrating the PWM waveform that's going into the fan. So it's a 25 kilohertz signal whose width I can vary, and this is right now at about a 30% pulse width. Now this one over here, if we move down here, you can see there's another oscilloscope here. It's a little harder to see, but this is the tachometer output from the motor, so it's kind of a square wave, and it's going to give 2 pulses per revolution of the motor. And down over here, I've got the signal generator that I'm using to create the waveform, and I've set it right now so I can adjust the duty cycle of it and thus change the speed of the motor. And at the back over here, there's a power supply that we're powering it, and this is a 5-volt motor, so everything's being powered by 5 volts. And the only other component that's at work over here is there's a pull-up resistor on the side of the tachometer. So let me just get this so you can see both of the scopes right now, and I'll change the duty cycle of the waveform. I'll make it wider. And as I'm making this wider, I think you can see that the other scope over here is getting narrower. In other words, the frequency is going up, and that makes perfect sense because that's, as I said, giving 2 pulses per every rotation of the motor. So now we're running pretty well at about full speed, and we can bring it back down. And again, if you notice the other oscilloscope, when I'm doing this, the frequency is reducing because the motor is going slower. Now, another thing that I want you to notice, and we'll just make sure you can see this scope over here, I'm going to stop the motor. And look at that, there's no waveform whatsoever. The motor is stopped. Now it's starting again, and you can see the waveform coming up. I'll do that one more time. And there you go, it's starting again. And so that's actually a good indication if the motor has stalled. If you're not getting any signal from the tachometer at all, it means it's not spinning. And so that basically illustrates the operation of a PWM controlled fan. And so now that we've seen how a computer fan works, we're going to get on with an ESP32 to see how we can control its speed. But before we do, I want to mention something about the 2-pin and the 3-pin fans. You're going to see a few YouTube videos and a couple of articles on the internet that claim that you can do speed control on these fans as well. And that is sort of kind of true. Some folks have found that by regulating the voltage going to the fan, that you can control its speed. And you can to a small degree, but that's not a particularly efficient way of doing it. Other people say that you can use pulse width modulation, and while that does kind of work, it only kind of sort of works. What you have to remember is that you're not powering a motor here. You're powering an electronic speed control that in turn is driving a motor. For example, I've seen some articles that say that you should put a diode across the power supply to prevent any flyback voltage from coming. That's a common thing that happens with DC motors, but it doesn't happen with these because these are brushless DC motors, and any of that EMF suppression has already been done on the ESC, so it's not necessary to put a diode across it. And also controlling the speed that way, even with pulse width modulation, doesn't really work. What you're essentially doing is turning on and off an ESC rapidly and hoping that will regulate the fan speed. So if you really want to control a computer fan, you're going to need to use a 4-pin fan. They're very common, they're not expensive, and that's what we're going to be doing right now. We're going to get out an ESP32, hook it up to a fan, and control its speed. So here's how we're going to do the hookup. We'll be performing our experiments with an ESP32 board, and you could use pretty well any ESP32. I'm using a Arduino Xiao ESP32S3 board because it's very inexpensive and also very tiny. Of course, the whole purpose is to rotate a PWM fan, so you're going to need one of those. Any 4-pin fan that's either 12 volts or 5 volts would be fine for this experiment. And you'll need a power supply for that fan, so if you have a 5-volt fan, get a 5-volt supply. A 12-volt fan will require, of course, a 12-volt power supply. And we'll need a potentiometer. I'm using a 10K linear taper pot, and that'll work well. Any value of 10K or higher should be fine. We'll begin by connecting the ground connection on the fan to the ground or negative side of the power supply. The positive voltage side of the fan will go to the positive voltage side of your power supply. Make sure you note the pinout and not the color code, because not all fans use the same color code. The tachometer connection on the fan will go to the Arduino Xiao pin D1. And the PWM control pin on the fan will go to the Xiao's pin D2. We'll connect the ground from the Arduino Xiao to the same ground we used for the power supply. We'll also connect the left side of our potentiometer to that same ground point. The wiper of the pot will be connected to analog input A0 on the Arduino Xiao. And the right end of the potentiometer will be connected to the Xiao's 3.3 volt output pin. And this completes our wiring. Now let's go and take a look at some code we can use to drive our fan. And here's the code that we're going to use to control our PWM fan. And it's actually pretty simple code. We start off by defining the pins, and you'll note that we've connected the PWM pin to pin D2 in the Arduino Xiao. That's actually ESP32 GPIO pin 3. So we use a value of 3 over here for the PWM pin. And the potentiometer is on address pin A0. We can use A0, and just for reference, that's GPIO pin number 26. Now over here we have the settings for the pulse width modulation. We've got the frequency, which is 25 kilohertz, so we've got 25,000 over here, and 8-bit resolution, so a number from 0 to 255. Now we go into our setup. We'll start our serial monitor, and then we'll configure the pulse width modulation. And the way that we configure that is we do an LEDC attach, and this is actually meant for driving LEDs with pulse width modulation, but it'll work with anything really. And so the parameters we provide are the pin number, the frequency, the 25 kilohertz, and the resolution, the 8-bit resolution. And then we're going to actually write to it. We do an LEDC write, and we'll write to that pin and set to a value of 0, which will halt our motor. So we're going to start off with a value of 0, and this is how we continue to control the speed. The second parameter here is actually the pulse width. And then we'll print the serial monitor, and we'll exit off of the setup and go into the loop. And the loop is really pretty simple. We're going to read the value from the potentiometer pin, and we're going to convert that into a number between 0 and 255 with a map command, and we'll apply that PWM to the fan. So again, we do an LEDC write with the PWM pin, and then fan speed, which is going to be the pulse width, the value of 0 to 255. We'll calculate and display that percentage, and then we'll write a whole bunch of those values out to the serial monitor, put in a small delay, and do it over and over. So again, it's a pretty simple sketch. Let's load it up and watch it in action. And so here's our simple fan setup on a circuit board, and if you look carefully in it, you can see my Arduino Xiao buried back there. Here's the pot, obviously, and again I'm using this power supply to supply the 5-volt power that's required by my fan, which is suspended over here. And so if we look at the serial monitor now, it says the pot is at a value of 0, PWM is at 0, and the speed is at 0%. Let's increase it a bit. And you can see the fan start to move, I believe. And if you look on the serial monitor, as I increase the pot, the PWM value goes up, and so does the fan speed percentage. And we'll increase that all the way to maximum. And that's the maximum right now. And we can set it back down if we want to. Regulate it till it's really, really slow, and then turn it off. And so the speed control seems to work just fine. So let's move on and see what else we can do with the PWM fan motor and the ESP32. The tachometer output on the computer fan typically outputs 2 pulses per rotation, and you can use this to measure the fan's RPM and display it. Another use for the tachometer output is simply to tell if the blade is really spinning. If the blade gets jammed by something, if it gets clogged up with dirt, it can stop spinning and it'll start taking a lot of current. And you can use the tachometer output to monitor this condition and then stop driving the fan in this case. So what we're going to do now is take the ESP32 code that we use to drive the fan and monitor the tachometer output. And here's the updates to the sketch that we're going to make in order to read the tachometer from the PWM fan motor. And we're going to start off in a similar fashion to the last sketch. We're going to add the tack pin, and again notice that although it's on D1 of the SHAO, it's actually GPIO pin 2, so we're going to use a value of 2 over here. The PWM settings are identical as before. Here's some variables for the tachometer. First of all, a variable to count the number of pulses that we're going to get back from the tachometer pin. Another variable to measure the last tack time, the last time we did a sample, because we need to sample these over a period of time. And that sample time is this over here, 1000, which is 1000 milliseconds or 1 second. So we're going to count the number of pulses within a second and use that to determine the RPM. Now here's the interrupt service routine for the tachometer. Every time the tack sends a pulse, it's going to cause an interrupt, and we're going to call this interrupt service routine. So it's called tack ISR, and we're going to increment the tack by 1. So we're going to increment the pulse by 1. Now you might wonder why I didn't just do tack pulse count plus plus, because it's a common way of doing an increment. I actually had done that on the original time I wrote this and got a message back that this function is being depreciated. It'll still work, but apparently that's been depreciated. So this is an easier way of doing it that won't be depreciated in the future. Okay, now we're going to go into the setup. We start the serial monitor as we did before, configure the PWM as we did before, and now we have to configure the pin that we have the tachometer interrupt connected to, and we'll use a pin mode for that, and we're going to put an input pull-up on that, and that's essential because what this is actually is an open collector output inside the motor, and so you need to pull it up to the voltage level you need. Now we could have used an external resistor, but it's a lot easier to do it just in code. And then we're going to attach our interrupt, and so it's to the tack pin. We're going to attach that interrupt service routine, tack ISR, and we're going to do it on the falling edge of the pulse. We probably could have done it on the rising edge as well. Okay, and now we did what we did before, set the initial fan speed to 0 with an LEDC write command to set the pulse width. And we're also going to initialize the timing for our tack. So we're going to set the last tack time to the value of millis. And millis gives you the number of milliseconds that have elapsed since the ESP32 was either reset or powered up. So we'll continue to use this as a timer. And we're going to print out that we're ready to go and go into the loop. Now in the loop, we're going to read the value from the pod, convert it to PWM, and apply it to the fan, just as we did in the last sketch, and calculate the speed percentage. Now here's where the tack comes in. We're going to calculate the RPM every second. So we're going to put the current time as millis. So now we've taken a second millis timestamp, and we're going to measure the interval between the two of them. And once it gets to the tack sample time, which is 1000 milliseconds or 1 second, we'll go into here and we'll calculate the RPM over here. Now we get 2 pulses per revolution, so this will calculate the RPM based on 1 second of sampling. And we're also going to estimate the target speed, because these fans have a maximum speed. In the case of the one I'm using, it's 5000 RPM. So you're going to plug that value into here. If yours is different, you can adjust it. This is a fairly common value. We'll display the results on the serial monitor and reset the counters then for the tack. We'll set the counter back to 0, and the last tack time is the current time. And then we'll put in a small delay and do everything over and over again. So it's actually a pretty simple sketch. We've added that interrupt service routine to hold the tachometer. Let's load it up and watch it in action. And so now we'll test everything out with the tachometer, and if you look on the serial monitor, I've got the pot all the way at one end, so the speed is 0 and the actual speed is 0. And let's start it up. And as I increase it, you'll note that the RPM goes up. We get the actual RPM and the target RPM. And I'm bringing it up past the 50% point. And here we are at 100%, achieving 4620 RPM according to our tack. And we can bring it down. And so that seems to work pretty good. We're able to control the speed and get the tachometer readings back. So now let's take everything that we've learned and build a really interesting project. Okay, so now we've come to the point where we're going to put together our project. As I said, we're going to create a temperature-controlled fan. And so we're going to add an LM35 temperature sensor to our circuit, as well as an OLED display that we can display things like the temperature and the fan speed. We'll also be tagging an LED along, and this will be an emergency indicator to indicate that the fan has stopped turning. And when it does stop turning, we'll stop applying pulses to it to stop trying to turn it. And so this will be a useful project in any case where you would need one of these computer fans. So let's go and see how we wire it up. To build our project, we'll keep the wiring that we've already used for our experiments and add a few extra components. We're going to be adding an OLED display. This is a standard SSD 1306, a temperature sensor, the TMP36, an LED to indicate a stall condition, and a dropping resistor for that LED. I'm using 150 ohms, but anything from about 100 to 220 ohms will work just fine. We'll begin by connecting the SDA connection on the OLED to the SDA connection on the Arduino Xiao. And we'll connect the SCL connection on the OLED to the SCL connection on the Xiao. We'll connect the VCC on the OLED display to the 3.3 volt output of the Arduino Xiao, and the ground on the OLED display will be connected to the ground. The positive voltage side of the TMP36 will be connected to the 3.3 volt output of the Xiao. The analog output pin on the TMP36 will be connected to the Xiao's analog input A3, and the ground pin on the TMP36 will be grounded. Finally, we'll connect the LED's anode through the 150 ohm resistor to pin D8 of the Arduino Xiao. The cathode of the LED will be grounded. And this completes our wiring. Now let's go and take a look at some code we can use for our temperature-sensitive fan control. And so here's the code that we're going to be using for our PWM fan controller with a temperature sensor. And the code is a little longer, of course, than the code we've used earlier, but I think you're going to see a lot of the same parts that we've used earlier, so it's not that difficult to understand. Now this is going to control the fan with a temperature sensor. We're going to set a minimum threshold to turn the fan on, and we're going to set a maximum threshold, and it'll go to full speed, and anything in between those two thresholds, it'll be a variable speed. The fan is also going to have a manual mode, and that's why we're keeping the potentiometer in the circuit. If the pot is all the way down at the 0 side, you're on the automatic mode, but as soon as you move the pot up, it'll be in manual mode, and you can use the pot to control the speed. It also has a fail-safe if the fan blade happens to be stopped, or if the fan blade is going slower than 30% of what it should be turning at. So there's a lot of code in here, but again, you've seen a lot of it before. Now we'll start by including some libraries, and these are all for the OLED, and some pin definitions, some of which you've seen before, a few extra ones like the temperature sensor and A3, and the LED, which is GPIO pin 7, which is the D8 pin on the Arduino Xiao. Here's some settings for the OLED, some PWM settings, which you've seen before, some settings for the temperature control, and this is where we establish the two thresholds. I've got it at 35 and 60 degrees Celsius, and you can, if you wish, go ahead and change that. The tachometer variables, similar to what we've seen before, and some other system variables. The interrupt service routine for the tachometer is identical to what it was in our TAC experiment. It'll increment the counter every time it gets a pulse from the tachometer. And we'll jump into the setup now. We'll start our serial monitor, initialize I2C, and initialize the OLED display. We'll configure PWM as we did before, and configure our pins. The TAC pin before has got an input pull-up resistor, and the LED pin is of course an output, and we'll also write a low to that to make the LED go off when we start. And here we set up the interrupt for the TAC as we did before. We write to the fan and set it to 0 speed and initialize a timing variable as we did before. Print to the serial monitor, and we're out of setup and into the loop. Now in the loop, we're going to read the temperature from the TMP36, and this outputs 10 millivolts per degree Celsius. So we're going to read the temperature and convert it. We're going to check for manual mode on the pot. Now if the pot is down near the bottom, we'll be in manual mode. We'll look for a value of under 100. Remember, this can go to 4095, so 100 is pretty small. That allows for any discrepancies in the pot and any noise. And if it's below 100, we're in manual mode, and then the fan speed is the same same as it was before in our previous experiments. But if we're not, then we're in automatic mode. Manual mode becomes false, and we take a look at the temperature, and we see if the current temperature that we're getting from our sensor is less than that of the fan on variable that we set. And if it is, then the fan's going to be off. If it's greater than the full speed or equal to it, the fan's going to be at 100. And if it's in between the two of them, then we are going to map the fan based upon the current temperature, as we do over here. Converting the percentage to PWM value, again, we've done that before. This is calculating the RPM, which we've done. We're also checking for a fan failure, and we're looking to see about the fan being below a certain percentage of what it should be at. We'll see if the fan failure is true, and then if the fan failure is true, we're going to set its speed down to 0 and the fan percent to 0. We're going to reset the counters at the end for the tachometer as we did before. And we'll apply PWM to the fan only if there's no failure. So if it's not a failure, we'll apply the PWM, else we're going to set it to 0. So that's a double protection to make sure the fan doesn't move if we encounter a situation in which it's jammed or something. We'll also set the LED on if the fan has failured, and that's what we are going to do in this line over here. And we'll update the OLED using a routine called update display, which you'll see in a moment. Is this below this? We'll send everything to the serial monitor as well to monitor things and put a small delay in. Now, here's that update display function. It basically clears off the display, puts the title on the top of it, and prints out things like the temperature, the fan speed, the RPM, and a status indicator, whether it's on failure, whether it's in manual mode or auto mode. We also create a bar graph to indicate the temperature because it's kind of cool. And then we go and display everything. And that's basically the code. So let's just load it up and see how it works. And here we have our final product, our temperature-controlled fan. And as you can see, I kept it on the same breadboard. I just added an extra potentiometer, the OLED display, and this is the LED that'll indicate if the fan has been stalled. I put the temperature sensor on its own separate little breadboard here. I'm still powering everything from the 5-volt breadboard power supply. I just had to move that onto a separate solderless breadboard. You can see I'm powering the same fan, which is off at the moment. And if you look at the display, the OLED display, it tells us the temperature is 27 degrees, and the fan is in automatic mode, and it's not turning because we set our threshold to 35. Now, if I turn this, I can go into manual mode. You'll see it went into manual now, and I can set the speed, and it'll read the RPM. And so I can manually set it anywhere I want. Now, if I stall the fan, I'm going to stall it, and you'll note that the fan blade is stopped now. The light has come on, and it's going to retry to go and see if it can go again. And after the retry, there's no stall, so it sends the fan on its way again. So this is a feature in case the fan gets obstructed or gets too clogged with dust or something. Now let's put it back into automatic mode by turning it all the way down, and we're into auto mode. And see if we can maybe coax the temperature up a little bit here. And there we go, the fan is turned on because we've gone over the 35 degrees. And of course our fan is going to stay on until that temperature drops. And you'll see that the speed is dropping now that the temperature is dropping as well because it's in a variable temperature zone. And so of course you can set those thresholds to anywhere you wanted. 35 might be a little bit low for some equipment, but I just wanted to do that more for the demo so I didn't have to heat it up too much. And so there you go, a temperature controlled fan based upon an ESP32 that you can build for your power supply or computer projects. Okay, well, that about wraps up our video for today. I hope that you enjoyed it, and even more importantly, I hope you learned something about controlling computer fans that you can apply to your next computer fan design. Now, if you need some more information about this, or if you want to grab the schematics or the code that I used today, you'll find all of that on the article that accompanies this video on the DroneBotWorkshop.com website, and there's a link right below the video to that article. When you're on the website, if you haven't yet, please consider signing up for my newsletter. It's not a sales letter, it's just my way of letting you know what's going on here in the workshop. It's free to sign up for, and all I need is your email address for that. But if you're willing to give me a little more than your email address, such as your first name and a crazy username that you dreamed up, then you could join the DroneBot Workshop forums and discuss electronics, fans, and all sorts of things with other like-minded individuals, and it's free to sign up for the forum. And another thing that's always free to sign up for, and I'd really love if you did it, would be to subscribe to the YouTube channel. It's very easy to do. Just click on that red subscribe button and also click on that bell notification. And assuming that you've enabled notifications in your browser, you'll get notified every time that I make a new video. So until we meet the next time, please take good care of yourself. Stay safe out there, and I'll see you soon here in the DroneBot Workshop. Goodbye for now.